This is a lesson covering the principles in the Introduction to Relativity. I'd covered relative motion before in kinematics, the basics of kinematics, and what we learned there is that there are reference frames. Each reference frame is a set of 3D Euclidean axes and a clock. And I say Euclidean, that means just flat, normal space, the way we think about space. And so if we want to measure something at point P, maybe it's moving, maybe it's not, we can locate it with our axes. We can also say what it's doing at different times with a clock. And we can have different reference frames. So like maybe over here, I can have x2, y2, and z2, and you can see it's at a different orientation, and it may even be traveling at a speed relative to the original axes here. So those are reference frames. There's no absolute reference frames. When we think about these two reference frames, there's no preference over one than the other. And what we see is that we only care about this relative speed between the two. Finally, what we're looking at in terms of relativity is observers in different reference frames moving relative to one another will measure the same motion with different values. So if there was a person over here in this reference frame and saw an occurrence happen in the second reference frame, that they would see a different thing going on than a person in that second reference frame. So observers in different reference frames will see the same motion with different values. And so that's what relativity studies. Relativity is the study of how different observers measure the same event. And you can see over here I included more of a modern conception of space. You can see that it is sort of like Euclidean in the way we think about it, but it's not flat. What we see is that mass distorts the shape of space-time, and there's some curving going on, and we have evidence for this curving. We look at stars that go behind planets or other stars, and their light bends around. If there's light, it can bend around an object, which is a very interesting effect and consequence of this bending of space-time. So what you need to know about relativity is that Galileo and Newton, Newtonian physics, Newton's laws, developed the first correct version of classical relativity. And when I say classical relativity, I'm talking about the things that I talked about in the relative motion, where I'm looking at relative motion between a couple of objects. The scientists got that correct. What they did not get correct is some of this other stuff that's going on that we're going to talk about in this lesson. And that was Einstein and his thought experiments. He was very keen about this idea of relativity. Not only the special relativity, but also the general relativity. He was really out there and on point on a lot of that stuff. So what do I mean by special relativity and general relativity? There's the two terms here. Special relativity is very specific in that the observers whose relative motion is at uniform velocity. That's special relativity. So it's a simplified case. That's special relativity. Whereas general relativity takes into account all cases. And what we see is that there could be accelerated motion under that. And we introduce a few terms here, inertial and non-inertial. So inertial reference frames is reference frames in which Newton's laws of inertia are valid. So we're looking at Newton's laws of inertia. Newton had a lot correct in his laws about acceleration, and because this frame is not accelerating, we can take into account any acceleration according to Newton. And so that's why we have Newton's laws of inertia valid in inertial reference frames. When we have some sort of otherwise accelerating that is not taken into account by Newton's laws, that's a non-inertial reference frame. And that's a lot of why we as humans have trouble figuring out, like, is space expanding or contracting? Because we're attached to space and everything's sort of accelerating, we don't have a good idea. And what I will say is that general relativity, right, this is general relativity, is the everyday case of human situations. We are accelerating. We're on a planet, we're in a galaxy, we are in a cosmos, and things are going on. We're moving around on space-time. We don't know it all the time. But on the surface of the planet, these effects are too small to be appreciable. We can't really tell. So this idea of general relativity, even special relativity, is sort of out of this world because we're not used to experiencing these effects, but they are there. So let's lay down a few postulates for special relativity. These are very important, and these are Einstein's two fundamental assumptions that he started out with. So what we're going to assume is that the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. So that's non-accelerating, right? Constant velocity. And what we're going to remember is that a reference frame is as good as any other in regard to the laws of physics. We have no preference for reference frame. If we do Newton's laws in one frame, we don't care if we do it in another frame. We see the calculations work the same and the consequences are the same, the predictions are the same. So all laws of physics are relevant and work the same in all inertial frames of reference. The other thing, which I think is weird to get used to, I've been working with it for many years now, and I anticipate it may be something that you forget you know, and that's why I put many problems in the homework regarding this. So that's why I put this here. The speed of light, c, is constant in every reference frame independent of relative motion. And I put the value of c here. And the consequences of this is, they're kind of creepy. Okay, because it goes against, like I said, our everyday intuition about our Earth experiences. So what this is saying is, if I drive my car, and I drive my car at 80% of the speed of light, if I get going really, really, really fast, right? And I turn those headlights on, you would think that the light from those headlights would go the speed of light plus that 0.8 the speed of light that I was going. Like they would get this extra boost of velocity because the source that they were emitted from was also moving. But it turns out the speed of light is c no matter what reference frame you measure it in. It's always this value. So if I see light in one reference frame, I'll measure it as c. If I see light in my reference frame, I'll measure it as c. Light will always have the same value no matter what reference frame. So I don't know if there's some sort of comfort in that. That makes sense. Like light is something that's fundamental for us and that it has a constant velocity regardless of reference frame. But it makes it hard to do math. To think about the consequences of this is actually creepy. And so the example that I brought up from Hewitt Conceptual Physics, the 10th edition, and this is this very simple example that leads to the derivation of the math around special relativity. And what this is a person who's sitting in a spaceship, and you can see that there's a spaceship, and we can imagine that the spaceship is going pretty fast. I'll put 80% of the speed of light here. And the person in the spaceship shoots a light to a mirror and back again. The light travels up and then back, and him in the spaceship sees the light travel that path, just straight across and back again. But we're smart. We know about relative motion. If I look at this second observer who's observing from sort of another reference frame, right? The spaceship goes speeding by, and instead of seeing the light go straight across, the person watched the light go from one side to the other, and it forms this path, okay? And this makes sense if I see someone driving past in a car and they throw something in the air. It'll look like it goes up and down to the person in the car, but to me, on the ground, it'll look like the path was parabolic. The speed of light is constant. This person sees this light travel speed c. But what we also know is this person sees the light travel this speed c. And this light clearly travels a longer distance than this light here. So there's a conflict going on. How can this event, right, happen that each person sees this light travel with the speed c? And not even taken into account that there's some sort of relative speed of this spaceship. So what we do, this is how we think about it, is that there's a consequence that is very important. And here's the derivation of this. I wanted to put the derivation here. And so I didn't derive it from scratch. Here's the path as viewed by the person in the spaceship. It goes straight across and then straight back again, and that is its path. The person on the ground, though, sees the light travel this path. And the only way to reconcile that is if the person in the spaceship experiences a different time than the person on the ground. The light travels the same speed. Both of them are c. And so what you see is this equation being created. This CT, where t is measured by the person in this reference frame, watching the spaceship, sees a different time lapse than the person in the spaceship. They measure a different time. The speed of light is the sound, but the time is different. And so that's how we can reconcile that there's this motion, this relative motion between the two. And what we get is just Pythagorean theorem, and we can write that out here. The hypotenuse squared, so this is the hypotenuse squared, equals a squared plus b squared, right? C squared equals a squared plus b squared, and that's side of a triangle, not the speed of light. So we put in what we know about each side, the hypotenuse, the short side, and the long side, and we can work that out. So we move that to one side, and we solve, and we get t on one side and t naught on the other. So this time is the one measured by the watching frame, right? This is the watching frame, the time in the watching frame, and this is the time in the frame where the event is actually happening. So this is where the event is. Stationary with respect to the event. Stationary with respect to the event. And so this is the equation we get. It's a very simple sort of derivation. It's just Pythagorean. But we had to assume one thing, that these two observers experience the same event in two different time periods. And that is where we on Earth would not necessarily think about this. The math suggests it. And so this is where the math goes, is there's a dilation or contraction factor. And it's given by this value. And you can see where it comes from in here. 1 over this radical here. That's what we call the Lorentz factor. It's a dilation or contraction factor. You'll see that with length in a second. And it's calculated with this relative speed in here. V is the relative speed between the two reference frames. C is the speed of light, as we know the speed of light. And this factor is always greater than 1. And I put this graph over here from Hewitt that shows as the speed of light increases, and notice that there's a maximum speed, right? At this point in physics, the speed of light is the maximum speed anything can get to. It is related to relativistic momentum and relativistic energy. Nothing can get as fast as the speed of light other than light. If it has mass, it can never get the speed of light. So we see as speed increases, as it gets closer and closer to the speed of light, this gamma factor increases greater than 1, okay? So you, in order to get like 3, 4, 5, 15, 30, you have to get really close to the speed of light in order to have a gamma factor that large. So when we look at the relativity of time dilation, so that's what we're looking at here. When these two people see an event happen, two different time periods, they describe the same event with two different time periods. That's what we call the relativity of time, and we refer to it as time dilation. A moving observer will measure a longer time than a person at rest with respect to the clock. And we saw that here. The person watching the spaceship go through sees this path to be longer, measures a longer time for the event than the person in the spacecraft. And you can see that here. Here's a muon. The muon lifetime is very short, but a person on the planet watching that muon sees the lifetime of the muon as much longer. Time passes slower for an observer who is moving relative to the clock, so it takes longer. And so we see that this is a dilated time because gamma is always greater than 1, then this will be larger than the original. Delta t is going to be larger than the original. Delta T naught over here, this is what we call the proper time. This is the time measured by the person or whatever with respect to the clock. So a pion is at rest with itself. It measures its proper lifetime. The person watching it is moving relative to that pion. The person watching it will not observe the accurate, proper value of that muon's lifetime. That person will measure dilated time, which is what we call delta T. So this is the dilated time over here, and this is the proper time to begin with. So the proper time gets dilated by this gamma factor, and we get a larger time. So we're seeing a little bit creepy implications of this theory of relativity arising from the postulate, right? We always have to go back to what's the fundamental assumptions of any theory, and the assumption here is that the speed of light is constant in every reference frame. If that's true, then time must not be the same in every reference frame. So that's what we have. So we can look at this idea of simultaneity. And I will define simultaneity. Events are simultaneous if they occur at the same time in an inertial reference frame. So let's say we have this ship, and the person inside the ship shines a light, turns the light on and off, and the light leaves and hits the back end and the front end of the ship. And if it's emitted in the middle, it should take just as much time to go to one end as the other, and that's what the person inside the ship sees. However, the person outside the ship, because the ship is moving by, it's going to take a shorter time in order to get to the back and a longer time in order to get to the front. And the person on the ship would see these two light rays hit the front and the back of the spaceship at the same time, but a person on the ground does not. So a person in the spaceship sees it as simultaneous. A person outside the spaceship does not see it as simultaneous. Very weird, very weird. Events simultaneous in one frame will not be in another frame. And this is a purely relativistic effect. It seems like it's too creepy to be true, but it has been verified. I put this verification up here. In 1971, it was predicted way before this. But the event, the actual experiment, was very precise. We have 10 to the negative 9th seconds, a billionth of a second, right? In the air for 45 hours. So they put a clock in the air for 45 hours. They flew it around the world, and it showed accuracy to the prediction within error. Like it was something that they predicted. If we did this for 45 hours, we should see the clock in the plane be different than a clock on the face of the planet because of the relative motion. And it was true. Amazing. Very amazing. We also see that with muons, the rest life is 2.2 microseconds. If you just look at a muon in a muon rest frame, it's not alive. Its lifetime is not very long. But if we watch it come across the sky, it is much longer because it's moving quickly. There's a relative motion between that muon and the person observing it. And so there's going to be a dilated lifetime for the person watching that muon. And so that's how this gets reconciled. Observations that we had seen are now reconciled with the theory, and also the theory made predictions. So that's a very nice scientific theory. That's what we like it to do. So let's look at a problem real quick about time dilation. I wanted to run through a little bit of the mathematics here to get you used to working with the equations alongside the concepts. So I have the lifetime of a muon. It says, suppose a cosmic ray colliding with a nucleus in Earth's upper atmosphere produces a muon that has a velocity of 0.95 c, so 95% of the speed of light. Because we are working with relativistic effects and not at small velocities, we need large velocities. You're going to see these velocities as pretty large. You may need them to be about 5%. Anything larger than 5 to 10% of the speed of light. So that's our speed here, and it's in terms of c. I'm not going to calculate that value because you can see when I plug it into this equation, I have it over c, and the c's will cancel, and I'm left with just a nice fraction. So do not just multiply this out. You don't need to know the exact speed. It says the muon then travels at constant velocity and lives 1.52 microseconds as measured in the muon's frame of reference. You can imagine this as the muon's internal clock. So up here, the proper time in the muon's reference frame is 1.52 microseconds. It says, how long does the muon live as measured by an earthbound observer? So the person's looking at the muon, and we want to know, what is this dilated time? So what I'm going to do first is calculate the gamma factor. This is Greek letter gamma. I draw it in this way. I'm going to just put it in the equation. There's a lot going on in this equation, and so I suggest that you take your sweet time when you're working with this equation, when you're plugging numbers in, or when you're doing algebra. I see students make algebraic mistakes that are simple and seem intuitive, but they mess it up and then they can't get the right answer. So make sure you're doing all your algebra very slowly here. So gamma, when I plug gamma in here, the c cancels. I take 1 minus 0.95 squared, and then I square root that, and then I take the reciprocal of that. I expect it to be greater than 0, and when I calculate gamma, I get 3.202563. And you may want to pause for a second and make sure that you can run that through your calculator accurately. What I'm going to also note is that gamma is dimensionless. There's no reason, and when we look up in here in this equation, we can see that we don't want it to have any units. When we look in here, 1 doesn't have units, 1 doesn't have units. I do v over c, so those units cancel, and this is a completely dimensionless quantity. I'm going to take this quantity and plug it into the time dilated equation here. I'm solving for delta t. So delta t will equal gamma times t naught. So I'm going to put 3.202563 and multiply by a delta t. So I'm just going to put in the 1.52 microseconds. I'm not going to convert it to seconds. I'll just leave it like that. And so I get, for the delta t, I get 4.8679 microseconds. We can see that the person observing the muon thinks that the muon lives a lot longer than what the muon actually experiences. And I'm bringing this up because one of the bigger topics, one of the bigger implications that's talked about this, because it's interesting, is the idea of the twin paradox. The twin paradox says that we have a pair of twins. One stays on the planet Earth, and the other takes a long trip in a spaceship across the galaxy, wherever she wants to go. I'm fine with it. And notice that at that point in time, the clocks are synchronized. They both read 0. At some point later, the person who is traveling returned, and she measured a time, and it was whatever time it was, right? The person on the planet, though, says you've been gone a long time, because that person was moving relative to the person in the spaceship. And what you will see is the twins, and I'll put an apostrophe here, the twins' biological processes occur at the same rate in 2 different reference frames. So it is true, they're the same, they're identical. Their biological processes, their rate of aging is the same. The one twin in the spaceship measured a time smaller and thus did not age as much as the person who stayed on the planet. This is a real effect of relativistic motion. And we saw that again with validating the 45 hours in an airplane. This is a real effect that happens. If a person leaves and then comes back, the people on the planet have aged much longer than the person moving in this spaceship. Very fascinating implications. Another implication here, and I find this isn't as difficult for students to comprehend and kind of latch onto, is length contraction. An observer moving with respect to an object will measure a contracted length than someone at rest with respect to the object. Let's look at a little example here that I had on a prior slide. Here's a person. The person on the ground sees the spaceship moving by. And remember, this is a pretty fast spaceship. Let's say 80% of the speed of light, going by quickly. The person on the ground is going to measure that spaceship as shorter. As they see the two ends, as they measure the two ends of something moving, they will not be able to measure it in the same way as a person actually on that spaceship. And what they actually get is a contraction. Notice I'm going to take the proper length. This is the proper length, L naught, and you will see that consistent with the time. The proper is designated with a naught, and then the dilated or the contracted, the changed, in this situation, this is the contracted length, is shorter than the proper length. We divide by this gamma factor. Remember, gamma is always greater than 1, so we're going to get a contracted length. And what I'm going to note here, you may see this in problems. I have a problem I like to give about it. Note that length contraction happens only along the direction of motion. So the person will see the ship shorter in this direction, but not in this direction. So we're going to have a length contraction here, but not in this direction. I will say at this point, I do caution you to be very careful. I find students have a hard time identifying the proper time or length and then the contracted length or the dilated time. They can really struggle identifying what is the proper and what is the dilated or contracted. And what I will say, this is my tip to you, is the proper is always measured at rest with respect to the event. So you ask yourself, who is at rest with respect to that thing? And that's the proper time or length. I've chosen an example problem, the fast astronaut, in order to exemplify length contraction. It says, suppose an astronaut travels so fast that gamma is 30. And if you remember that chart, that's like off the chart. So they're going really, really, really fast. She travels from Earth to the nearest star system, Alpha Centauri, which is 4.3 light years, and so there's the symbol for light years, away as measured by an earthbound observer. How far apart are the Earth and Alpha Centauri as measured by the astronaut? So we really, like I said, we really have to think about who's at rest with respect to the event and who is moving with respect to the event. I also chose this problem because it talks about light years. And what I'm going to tell you, I'll write this up here, a light year is a distance. It is not a time. I know it has the term year in it. The light year is the distance light travels in a year. So it's a distance. It's definitely a distance. It's not a time. So don't put light years into the time equation. Make sure you're using the length equation. And so I'm asking myself, so here's Earth and here's Alpha Centauri, and there's some sort of distance between them, some proper distance between them. And I ask myself, who measures that proper distance? The person at rest with respect to both of them is going to measure the proper distance. When I think about the person in the spaceship here, there they are, they're moving with some speed relative to this distance. The person on Earth is at rest with both of these. So the person on Earth is going to measure the proper time. It says Alpha Centauri 4.3 light years away is measured from the earthbound observer. So we're going to measure the proper distance, the proper length is 4.3 light years. Okay. So now that we have that, we have gamma, we're given gamma, we have the proper length, so we can find the contracted length. So we're going to put 4.3 light years in here and divide by gamma, which I know is 30. And so the person on the ship thinks that the distance, measures the distance between the Earth and Alpha Centauri as 0.1433 light year. Very short compared to the original, but they're traveling really, really, really fast. So when you're thinking about that, thinking about a particle traveling through space, they're traveling so fast they don't think that a distance is very far at all. And that is their true experience. The second part here says, in terms of c, what is her velocity relative to the Earth? So we're just going to assume that Earth is here and gamma is 30. And what we want to do is solve for v in this equation. I chose this problem just to exemplify some of the algebra that goes on in here so that you can get an idea. The first step I'm going to do is maybe square both sides, gamma squared. The first step I'm going to do is square both sides, gamma squared equals 1 over 1 minus v over c, quantity squared. I'm going to invert those because I'm isolating for v. 1 minus v over c, quantity squared, equals 1 over gamma squared. I'm still isolating v, so let's do v over c, quantity squared, equals 1 minus 1 over gamma squared. And finally, I'm solving for v still. I'm going to have to take the square root of both sides and then also multiply by c. So v equals c, the square root 1 minus 1 over gamma squared. Okay, so you may be asked for different quantities, and this is how I would calculate the velocity. V equals c times the square root of 1 minus 1 over 30 squared. Okay, so you'll run this through your calculator, plug in what you know here. I'm going to leave it in terms of c, like on the prior example that I did, it was in terms of c, so we get a velocity that is 99.94% of the speed of light. It's very, very close to the speed of light, but I already predicted that because I knew that the gamma factor was so large, we would have to be going very close to the speed of light in order to get a gamma factor that large.